Hello, this is Von Richter for Homework 1, Linear and Nonlinear Regression of Anton's equation. On the left, I have a PDF outlining the layout of my method for determining the design matrix and how it's going to work on the code itself. I just thought it was better to lay it out this way as opposed to trying to verbally explain it while coding. And then on the left side here, we have our GitHub site with all of the data we need for this submission, our water vapor pressure, as a .csv file. And then we have our Google Collaboratory tab with some functions already imported, such as numpy and plotly. I just added those as there's no real logic to it, and I am a very slow typer, so I figured it would save us some time. In addition, I have some text blocks in between to kind of structure what we're going to be talking about. First, we'll be talking about our linear regression. That was kind of walked through by Garrick. And then our import of our data from GitHub, going through our design matrix, making a plot of all of our data, and then finally ending with an alternate method of nonlinear regression using the sum squared error method. So let's start out by taking our data from GitHub, getting these two columns of, looks like 26 rows of data, going into the raw file, copying the link over, and then calling on a wget, put an exclamation point beforehand, copy and paste the link over, and it looks like we had our vapor pressure, or water vapor pressure .csv file transfer over. So now what we want to do is we want to take this data and we want to kind of clean it up a little bit. So we're going to call on numpy and use a function called load text. From load text, we're going to call on the water vapor pressure .csv file, and then we're going to use a delimiter to space out all of the values with a comma. And numpy, oh, okay, so I forgot to run the top. So after that runs, now we have numpy. And now when we run this, we should get, we get our array of data points. So we're going to store that as data. Wonderful. And now we're going to separate out our two columns. So our first column is our temperature data. So we're going to call T is equal to all of the rows of column 1. And then we're going to take our log P and set it equal to colon numpy log base 10 of our data of all rows and the second column, and run that. If it runs. Okay, great. So now we have our, essentially our X and our Y variables from our data set. So we could plot it now, but we're going to just move on and just show it on a plot later and just skip right ahead to looking at our design matrix. So kind of pulling attention towards the left side of the screen on the PDF, you see Anton's equation is designated by log base 10 of pressure is equal to your constants A minus B divided by quantity C plus your independent variable of temperature T. In order to get this into a nice fitting equation where we can make a design matrix and do some linear algebra in order to solve for the constants, we're going to do a little bit of algebra just to manipulate the equation a little bit until we get down to our T log base 10 of pressure is equal to AT minus C log base 10 of P plus AC minus B. So this is kind of just the result of doing some multiplication. But It's important to note that this AC minus B term is nothing but constants here. So what we can do is we can actually simplify the whole equation by setting it equal to a arbitrary variable D. This will just make things easier when we look at our design matrix later. And then that's just kind of reflected here in this next equation. But now putting this into a design matrix, we have our what we'll call our Y matrix of T log base 10 of P is set equal to a matrix X and V, X being T negative log base 10 of P and 1. This comes from the fact that our A, C, and D terms on this right side of the equation are all constants, and therefore are thrown into a different matrix of A, C, and D. Notice the sizing of these matrices, n by 1, n by 3, and 3 by 1. This comes into play when we look at manipulating these matrices by multiplying both sides by the X transverse matrices in order to get a nice 3 by 3 matrices on this side, and a 3 by 1 stays the same. And then over here, we change our matrices size to about 3 by 1. In doing so, we can also multiply by the, again, X transverse times our X matrices, and then take the inverse of that, and then again, matrix multiply by your X transverse and regular X. But you're going to also have to do that on the other side here. And what that's going to result in is this matrices with a, diagonal line of ones, and then columns of zeros. And what this is going to do is it's going to allow us to solve for our Antoine's coefficients AC and D. And D is really going to give us our B value, right? And this essentially is going to be set equal to actual data outputs that we're going to compute using Python or Google Collaboratory in order to get those constants, right? So now let's kind of walk through that in Python here on the right side. So first, let's start by creating an X matrices. So we're going to set X equal to a column of 3 different variables. So first we're going to call on our temperature T. Then we're going to take the negative log of our P, which we initialized here. And then we're going to have a column of 1. So what we're going to do is we're going to call on numpy to do numpy dot ones dot, it's an underscore like, and then we're going to set it similar to T, so we'll have the same size, right? So if we run that, we now have our X matrices. But now we need to get our X matrices to essentially produce our A, our C, and our D, right? Which is going to be on this side. So in order to do that, we need to be able to, one, use our X matrices in linear algebra, and then we also need to call upon our Y matrices, which is this T log base 10 of P. So more or less what we're going to do is we're going to copy this equation here on line 6 of the inverse of X transpose times X using matrix multiplication, then again using matrix multiplication of X transposed times Y. So in order to do the inverse of that function, we're going to do numpy linear algebra dot inverse. We're going to take the quantity of our X transposed with an @ sign indicating matrix multiplication of our X matrices, and then again matrix multiplication of our X transposed, doing matrix multiplication again of our Y matrices, which is actually a quantity of T times log P. In this case, we're not doing matrix multiplication just because that is what is actually our Y matrices itself. So, moving on, you notice that we have our A, C, and D, but like I said earlier, we're going to want to actually solve for our B. And in order to do that, we kind of just backtrack here to when we said AC minus B equals D. We're just going to manipulate that equation a little bit and have our B equal to A times C minus D. So now, when we run that, now we have all of our Antoine equation constants solved for linearly. So now let's just plot that to make that kind of sink in a little bit more. So first we're going to just add a figure, and we're going to do make subplots. Yep, and then we'll do that. Now we have to add some of our data. So we'll do fig.add.scatter. And we'll do our x variable is equal to our temperature, our t data. And then our y variable is going to be equal to our log p data. In order to get just scatter plot points, we're going to set the mode equal to markers. And then in order to just name the legend, we'll name it data points. And then we'll just get our figure object has no attribute to add. Oh, wait a second. One of these is probably an underscore. So we'll do an underscore. Wonderful. Okay, so now we have our data points running across our graph. But now we do not have our legend yet. Maybe we just need to add another point in order to get some of that data legend. So what we're going to do here is we're going to now set a trend line to be equal to our Antoine's equation. So A over here, A minus B divided by our quantity C plus T. And then we're going to set it to a mode of, in this case, lines, because we want that regression going across these data points that hopefully best fits. And then we'll call it name equals, and then since we'll be doing a linear or a nonlinear regression later, we'll just call this one linear. And we'll run. And invalid syntax, maybe this is just line. Oh, wait a second, I forgot my equal sign. So now we run this, and I did the same thing again. Figure add scatter, wonderful. So now we have our legend, and we have that linear regression going across all these data points. But you notice in between these larger gaps where we don't have enough data points to really get a nice fit in this like 400 to 350-ish range, we have these straight lines connecting these data points, which is going to happen based on the math we did. But maybe we can better fit that by creating a few more values that will fit across that line, as opposed to just using x values of the data points themselves. So we're going to make temperature or x-axis variables t-plot that have several more positions using numpy linspace. And then we'll do numpy min of t, and then numpy max of t. We'll do 100 points. Run that. And then we actually have to put it in. That would be helpful. So we'll do a t plot. Run. And now we have a smoother line. And now we can actually kind of fit this and say that this is a better fit to our data in these little gap points here. So now we have to move on to looking at our sum squared error method, which is essentially a nonlinear regression. So shown on line 7, you can see the sum squared error designated by SSE is the sum of your y model minus your y actual. In this case, I have it written out as mxi plus b minus yi. This model in this case is going to actually be your Anton's equation of a minus b over quantity c plus t. And then your y actual is going to be all your log p data that we already imported up here. And then what we're going to do after that is we're going to square that whole value. And the reason behind that is sometimes our y model is going to be lower than our y actual. So say our y model predicts slightly lower than this data point right here, which it looks like it does in the case of our linear regression. So that's going to return a negative value, right? But in order to accommodate for the overall error, which is going to be a positive number, you're not going to have a negative error, you square that value. So you won't run into any instance at which maybe one time the y model is lower than the y actual and one time the y model is higher than the y actual to the same degree, and then they end up canceling each other out. And you could potentially run into a situation where you have no error, but it's extremely, like if you look on it graphically, you can obviously see there is drastic error. So pretty much what this sum squared error method is going to do is it's going to take these differences and essentially measure the amount of error. And then we're going to call on our SciPy functions in Google Collaboratory. I'm going to return this to home. And we're going to call on that function in order to essentially minimize this error. And what that's going to do is it's going to be able to essentially look at our y model equation that has our Anton equation coefficients of a, b, and c, and constantly run through different values in order to best minimize this error so we get a better regression across our data and essentially get our constant values for Anton equations to be closest to what we observe from our experimental data, right? So let's go ahead and start that in Google Collaboratory. So first, we're going to want to import some of the functions we're going to use later. So our SciPy.optimize. And from that, we're going to import our function minimize, which is extremely helpful later. And next, what we want to do is we actually want to define our sum squared error function as SSE. SSE, we're going to call on a matrix V, which is very similar to what we did up here, where V will end up being, our A, our B, and our C values. In this case, we can skip the D part because D was essentially just a placeholder anyway. So A, B, and C will be equal to our V value, right? And then, why does it keep doing that? So then what we want to do is we want to return essentially this equation, right? So we'll call on NumPy to do a sum of our A minus B divided by quantity C plus T. And then that's going to be our y model, right? And then we're going to subtract by our log base P, which is our y actual. And now we want to take that whole quantity that we have there and square it. After squaring this, we now have a functioning sum squared error function. Unless you don't put a semicolon. Or colon, sorry. So now what we want to do is we want to minimize, so calling on that SciPy function. We're going to minimize our SSE sum squared error function. And the parameters we want to essentially guess for, we're going to have to guess for 3. So we'll throw in 2 commas there. For A, we'll guess around 40. For B, it's usually a higher number. We'll guess 2,000. And for C, it's usually like negative whatever A is. So we'll do negative 40, right? And then we'll run. So SciPy gives us all of these functions in return, but the only thing we're really concerned about is our X results. These X results essentially output what the true values for A, B, and C truly are, or I guess you should look at it here, A, B, and C. So what we want to do is we want to essentially store all those A, B, and C values. So we're going to take our minimize.x, so we only call upon this line, and then we'll pack them into A, B, and C. Although, so because we already used A, B, and C up in the linear regression, we're actually going to add a NLR to the end of all of our variables so that we can tell the difference between them when we graph. And then we run that. Now it's all condensed and nice. So we'll simply just add this up to this plot here. So we'll do fig add, and we'll use the one with our t-plot so that we get a nice fitted line again. But in this case, all of our A's are now going to be replaced, or A, B, and C is now all going to have our NLR extension so that we separate our variable. And then we'll change our name to nonlinear and run. So now it looks like our linear regression is essentially gone. We'll blow this up now that we don't really need the PDF. So now we can zoom in and kind of see what happened here. And what we're noticing is, zooming in at this data point, we can see our non-linear regression is just slightly closer than our linear regression. So this is just showing that our sum squared error method and minimizing that sum squared error is just going to get us slightly closer, at least at this data point. Maybe the other ones aren't as close, but in this case, we're getting a slightly better fit around this 463 area. And that is it for the Homework 1 submission. Thank you very much.